Lab session 5. In this session, we're going to discuss a machine shop problem. So basically, the objectives of this exercise is to learn first how to use the sys delay release blocks. Then you're going to learn how to use different type of sets, capacity sets, and sets with statistics, mainly counters and tallies. And at the end of the problem, we're going to learn how to calculate the number of replications. Okay, so I'm assuming that you have read the problem so far. So I'm going to give like a quick description of the problem. So let's start. Basically, in this problem, we have parts arriving. We know the distribution exponential with parameter 25. Once parts have arrived to our system, then we're going to assign with a equally likely probability that they are going to be assigned to machine 1 or machine 2. So it's like 50-50. So once these parts have been assigned to one of the machines, then they're going to join a single queue. So these two machines are equivalent. I mean, they perform the same process, but the processing times are different. So we need to consider that part. And in terms of the operation, okay, so once we want to process one machine, one entity or one part, so we need first to perform a setup. But for this setup, we need an operator. There is just one operator in the system. And we need the machine where we're going to perform the operation. So once we are done with the setup, then we have the process time. But for the process time, we don't need the operator. We need to release the operator, and we just need the machine. And once the process is done, then we need the removal. But for the removal, we need again the operator. So we need the machine and the operator in order to perform the removal. So there is just two machines, machine 1 and machine 2. They are different because the processing times are different. And there is a single operator that performs both operations, the setup and the removal. Okay, so let's start building the model. So we need to start with the create block. So it's a random distribution. The parameter is 25 minutes. That's the parts arriving to our system. So as I mentioned before, the idea is to use sets because we want to have a single queue. So now we need to assign, remember the probability, the 50-50 probability, whether we're going to process the part at machine 1 or machine 2. So we have two options. If you want to use the decide block, that's fine. Or let's try using a single assign. But for the sign, we're going to create an attribute. That attribute represents the number of the machine where the part is going to be processed. So I'm going to call it mem, like member. Okay, so we want to give probability 50-50 that the part is going to be processed at machine 1 or machine 2. So we're going to use a random distribution, a discrete probability disk. So the way this distribution works is that first we assign the probability for the first value, then the value that we want to assign, in this case is 1. 1 represents machine 1. And then we have this one, it's the cumulative probability. So basically it's a probability of 0.5. And the value that we want to assign given the previous probability. So in this case, we need to assign values of 1 and 2 because we have two machines, machine 1 and machine 2. But if you, in general, if you want to use a different name here, a different number, that's possible. Okay. So far we have assigned the member or the machine where the part is going to be processed. Now we need to create the arrival time. That's mainly because in the statistic that we want to find, at the end of the model, we want to calculate the cycle time. So we need to know at what time the part arrived. So let's call it arrival time. And the value that we're going to assign is t now. Okay. So once we have assigned the machine, so now we proceed to our process. But in this case, please notice that the process, it's not a traditional process because the resources that we need changes. I mean, initially we need the operator and the machine, but then we just need the machine, and at the end for the removal, we will need both again, the operator and the machine. So those changes in the resources, we cannot capture them using a single process block. So we need the sys delay release in order to capture those changes. So let's start with the initial sys. So in this initial sys, the idea is that we need to sys the operator and the machine that was assigned. So I'm just gonna call it sys setup because that's the first part of the process, the sys setup, and we need to assign the operator. We need one operator, and we need one machine. So the thing here is like we know that there are two machines, but we need to know which machine we're gonna use. So that's why we are gonna use a set. I'm gonna call it set of machines. So we need one member from that set, but we cannot use any member. We need a specific member because remember that we have assigned previously an attribute to represent to which machine that part has been assigned. So that's why we need the logic. The selection rule will be a specific member, and the set index, it's the attribute that is gonna make reference to the machine that we're gonna use. So in this case, if mem is equal to 1, that means that we're gonna use machine 1, and if mem is equal to 2, then we're gonna use machine 2. Okay? So now if we go to our processes and we check our resources, right now we have created the operator, but please notice that we haven't created the machine 1 and machine 2. So we need to go to sets. Even though we have the set, please notice that the number of members, it's 0 right now, it's empty. So we need to create two members here. So let's create machine 1 and machine 2. So now if we check our resources, now we have two new resources. And the capacity is it's 1. We just have a single operator. We have one machine 1 and one machine 2. Okay, so in this block we're syssing the resources, but please notice that in the sys there is no time involved. So if we want to represent the setup time, we will need a delay. So this delay will be for the setup. And we need the delay time. So given that we have like a single, let's say single queue, a single stream of entities, we need to use multidimensional expressions here. So we're going to the expression module, and let's create an expression for the setup time, an expression for the process, an expression for the removal time. So the first one will be setup time. The number of rows means the number of expressions that we're going to have, how many rows. So in this case, we're going to have 2 rows or 2 different distributions. So for the first value, we just need 2. So for the first value, we're going to assign the triangular distribution, and the parameters are 8, 11, and 16. This is the distribution for the setup time in machine 1. And now we need the setup time if we are in machine 2, which are 5, 8, and 14. Now we need to create a similar expression, but for the process time and for the removal time. Let's call it process time. Two rows. Triangular distribution. And the values are 20, 23, and 26. For the second machine, triangular distribution, and parameters are 11, 15, and 20. And finally, we have a third expression for the removal time. Two rows, same distribution, triangular, and parameters are 7, 9, and 11. For the second machine, triangular, parameters 4, 6, 8. Okay, so once we have used and once we have defined the expressions, now it's time to use them. So let's go to the delay. Remember that this delay is for the setup. So the delay time will be given by the expression that we have created for the setup time. Remember that we call it setup time. But it's important to notice that the setup time expression, it's like a vector. It has two possible values because it has two rows. So we need to make sure that we are assigning the correct row. So in general, remember that the row that we're going to use is related to the machine where the part is going to be processed. So that the attribute that captures the machine where we're going to process the part, it's given by the attribute member. That's the name, mem, that we have assigned before in the assign one. The units, it's minutes. Okay, so at this point we're done with the setup. So we're good to go to the process. But before we go to the process, remember that during the process, the operator is not required, it's not needed. So we need to release the operator. So this is the release for the setup. So we're going to release the operator. We don't need to release the machine. Why? Because the machine will continue the process. So once we have released the operator, we continue with the process. The process will require just a delay. This is the delay of the process. So the delay time will be given by the process time. Remember that we have created that expression before. And again, given that expression, it's like a vector, we need to mention the index. So the index will be given by the attribute mem again, and the units in minutes. Okay, so once we have performed the process, then it's time for the removal. But before we start with the removal, remember that we need the operator and the machine. So we need to seize again the operator. the resource, it's the operator. And remember in the problem description that we need to assign priority to the removal. So that's why I'm going to change the priority from medium to high. That was in our problem description. So once we have seized the operator, then we will be able to perform the removal. So that's a delay. This is a delay for the removal. And the delay time, it's given by the expression removal time. It's a vector, so let's use the index mem and the units in minutes. All right, so once we're done with the removal, so it's time to release our resources. So in this case, we're going to release both. We're going to release the operator, and we need to release the machine that it seized. So we need the release block. So let's release the operator. And let's release the machine. Remember that the machine is contained in a set. So the set name is set machines. The quantity is 1. And the release rule, it's a specific member. And the attribute is mem again. So here we're releasing from removal. And basically at this point, the part it's done, it's ready to leave the system. But before the part leaves the system, remember that we need to collect some statistics. So we need the cycle times for those parts that were processed at machine 1 and the cycle times by parts that were processed by machine 2. And we need to count the number of parts that were processed on each machine. So we will need a couple of counters here, a couple of record blocks. So let's go to the basic process. We're going to add a record. So this record will be for the first one will be for the cycle times. So the type it's time interval. So using which attribute? Remember that in order to find the time interval, we need the arrival time. And this is an attribute that we have created in the first assign. But given that in this record, we will have two types of parts that were processed at machine 1 and parts that were processed at machine 2, we need to record it into a set. So we need to assign a name for the set. So let's call it cycle time machines. And the set index, again, let's use mem. So now if we check the sets module, you will see that we have a set with tallies, but right now it's empty. So we need to add 2 rows here. So here, what is important, and in general throughout our model, is that the first row in general refers to machine 1 and the second row refers to information and variables associated to machine 2. So in the first row, this is the cycle time, M1, meaning that parts that were processed in machine 1. And the second row will capture the cycle time for parts that were processed at machine 2. Okay, so once we have recorded the cycle times, then we need to count the number of parts. So the type is count, value is 1, but we need again a set because we need 2 different counters. In case you don't want to use sets here, you will need like a decide block first and then a couple of assigns if you want to skip the recording into a set. Okay, so the name of the set will be number of parts. and the set index, it's mem. Okay, so now we go to our sets module and we need to create a couple of counters. So we need to assign a name, number, parts, machine 1, and number of parts, machine 2. Okay, so we have two members. So this record is for count parts. So once we have recorded the information for the cycle times and the number of parts, so now we need to dispose the entity. So this is our model so far. We have an initial arrival, random distribution, 25 minutes. Then we assign an attribute, we call it member, memb. Memb refers to the machine that is going to process our entity or our part. In this case, we're using a discrete distribution. So we're assigning a probability of 0.5 that the part is going to be processed by machine 1 and 0.5 that the part is going to be processed by machine 2. And we need to add also an attribute for the arrival time, because later we find the cycle time. Okay, so once we have assigned those attributes, then we seize the operator and the machine. Remember that we're using a specific member for the machine. This is for the setup. So then we have the setup time. Once we're done with the setup, we release the operator, but we still have seized the machine. So then we have the delay for the process, and then we need to seize the operator, because we need the operator for the removal. So once the operator is seized, then we perform the processing time or the removal time. That's a delay. And once we have finished the part, so we release both the operator and the machine. And at the end, we record the cycle time and the number of parts. Okay, so there are a couple of things that we need to adjust here in our setup, replication parameters. So the replication length, it's 25 minutes. The base time units, let's use minutes. And the number of replications for our analysis, in the project description, it's mentioned that we're going to use 10 replications. So we apply the changes, and once we're done, so we run our simulation model. Okay, so it's running for 10 replications. Let's check the results. So the number out, 761 parts. And the total time of the overall is 3236.08. Okay, so now let's go back to our program description, and we have a table, and in this table we have the statistic that we need to collect from our simulation model. So we need the mean value and the confidence interval at the 95%. Okay, so let's start with the number of parts processed by machine 1 and machine 2. So that's a user specified because we created a couple of counters. So here we have the number of parts for machine 1 and for machine 2, the average and the half width. So if we want to find the confidence interval, it's basically the average plus minus the half width. So let's capture the values. So it's 378.6 parts. For the average for the number of parts processed by machine 2, it's 382.50. We need the half width. So for the confidence interval, we need the mean plus minus the half width, 9.74. And for the number of parts processed by machine 2, it's the mean plus minus the half width, which is 12.22. Now we need the operator utilization. So let's go to resource, the instantaneous utilization. For the operator, it's 0.54. So the half width, it's almost 0. So I'm not gonna write down I'm not gonna type the confidence interval because the half width it's almost 0. Okay, now for the cycle time, that's a user specified. So the cycle time for parts that were processed at machine 1, it's 3,213.15. This value is in minutes. So we capture the confidence interval. The half width is 355, 93. And for part 2, the cycle time, it's 3,258.50 minutes. Plus minus the half width, 351.22. And finally, for part A, we need the overall cycle time. So for the overall cycle time, remember that we have a single create, so we just have one entity type because we are not changing the entity type at any point in our simulation model. So if we go to entities in time, we will find the total time. And that's for a single entity type, the entity 1. I didn't change the name that was assigned by default, so it's entity 1. Okay, so the average, it's 3,236.08 plus minus the half width for the confidence interval, that's 350.3. Keep in mind that value, the half width, the 350.3. Okay, so for part B, we want to verify the operator utilization. So we want to calculate the expected value, basically. So remember that the simulated value is 0.54. So we want to find, the expected value, and they should be close. So for that part, so in general, when we want to find the utilization, the first information that we need is the number of parts that were seized by the resource. So in this case, the operator will seize 1,524 times. But remember that we have two different processing times. I mean, the processing time is different if the part was seized by machine 1, or it's different if it was seized by machine 2. So that's why we need to break that value in two. So the number of parts that were seized by machine 1 and by machine 2. And we know that if we seize one part in machine 1, the operator is involved in two operations: the setup and the removal. The operator is not involved in the process, because the process is just performed by the machine. So basically, we need to find the expected time that the operator is used during the processing of parts that were assigned to machine 1 and parts that were assigned to machine 2. So we know that on average, or the expected value, if a part is assigned to machine 1, so the operator will be seized during this time, the summation of 11.67 plus 9.33. Same idea for machine 2. We need the expected value for both operations, and the summation of these two values will show us the amount of time that the operator was seized when it was processing one single part on that machine. Okay, so in general, we need the number of parts that were seized in machine 1 and the number of parts that were seized in machine 2, and we need to multiply it by the expected processing time. So we know that the expected processing time is the summation of these two expected values, that for machine 1 and these two for machine 2. So in this equation, the numerator represents the total amount of time that the operator was busy, or the expected amount of time that the operator is going to be busy. It's an expected value because we're using the processing times are expected values. So once we have the total amount that we expect that our operator is going to be busy, we need to divide it by the total amount of time on which the operator is going to be available. So we know that we're going to run the model for 25,000 minutes. So when we divide these two values, we get an expected utilization of 0.54 or 54%. So if we go back to our table, you will see that we have found the same value. So yeah, we were able to verify the expected utilization of the operator, and they are similar. Okay, so now for part C, we want to verify the 95% confidence interval for the overall cycle time statistic. We want to do this manually. Okay, so for the confidence interval, so we need to remember first the equation for the confidence interval. So we need the mean, which is given. We have this value for 10 replications, and then we need the t statistics. Then degree of freedom is n minus 1, where n is 10, because we have 10 replications, so the degree of freedom here is 9. Then we have the confidence level. For this problem, it's 95%, and we have to multiply it by S. S is the standard deviation, and we have to divide by the square root of n, where n is the number of replications, 10. So how do we find S, the standard deviation? So basically, we need to go back to our simulation model, and remember that we're running this model 10 times. We have 10 replications. So we have to go replication by replication, and we need to find the overall cycle time, the total time. For example, for the first replication, the average total time was 2,621.33. So we need to capture this value. Then we go to the second replication, and we find the same statistic, the total time. So the total time for the second replication, the average, it's 3,301.41. So we need to keep going replication by replication until we have collected the 10 average values. And once we have the 10 numbers, so we will have the average that is given in our overall report, and we need to find the standard deviation of those 10 values. That's the way that we find S. Okay, so for this problem, the sample mean, it's the overall cycle time that is given in the main report. It's 3,236.08. S, we need to find it. We need it's not provided by ARENA. We need to calculate the standard deviation, and then we need to find the T statistic for the degree of freedom and the confidence level that we want to provide. So we just need to plug the numbers then in our equation, and we will have that the confidence interval is the mean plus minus 350.3. That's the half width. So if we go back to our table, we will be able to confirm that we're getting the same interval, so our numbers are correct. Finally, in part D and E, in part D, we need to use PAN because we want to evaluate the overall cycle time given that we're going to change the number of operators from 1 and 3. We want to compare the base scenario where we just have a single operator and the scenario where we have 3 operators. So for this comparison, we're going to use PAN. So we need to go back to our simulation model. Let's save it. So I'm going to call it lab 5 model. I'm going to run it again because I want to make sure that you know that when you run the model, ARENA creates a lot of files. So I want to make sure that in the new location, we have those files. So I'm going to run the model and I'm going to save it again just to make sure that we have those files, because for the process analyzer we need the .p file. Okay, so I'm going to save. And now let's start using the process analyzer. We go to Tools, Process Analyzer. We're going to create a new file. And now we need to add scenarios. So if you want to change the name, that's fine. I'm just going to leave it as scenario 1. That's going to be our baseline. It's like it's part A. So for this new, for the process analyzer file, we will need the P file associated to our model. In my case, I call it lab5model.p. It's a MATLAB file. So once we have entered the file, now we need to add the controls and the response that we want to analyze. In this particular case, we want to modify the number of operators. Basically, we want to create scenarios changing the number of operators in order to measure the impact on the overall cycle time. So let's add the operator. So now we have an additional column for one control, and the response, it's our target variable basically. So we insert a response. So remember that our objective function here, it's like the total time, the overall cycle time. So that's entity 1 total time. So this is for the first scenario, but remember that we want to compare this scenario with a second scenario. And the main difference is that in the second scenario, the number of operators, it's 3. So now we want to check if there is a a statistical difference in the overall cycle time given that we are changing the number of operators. So let's run our models. So we need to select them and we run the scenarios. The process is asking to save, if we want to save the file. So let's save the file. So notice that it's running. This is the number of replications. So it's running for 10 replications and we get the overall cycle time here in this column. That's the response. So right now we have two values. For the first scenario, it's 3,236, and for the second scenario, it's 2,825. So maybe for you at home, it's easy to say, okay, no, then the second scenario is better. That might be true, but in general, we cannot generalize that. I mean, this is not like simple math where we just compare two values. Here we need a statistical analysis. So basically, we need a mean comparison. So the first step is to report the values in our table. So when we have a single operator, the mean cycle time, we already knew that it's 3,236. That's in our first table. And for the second scenario, it's 2,825.02. But now for the recommendation, remember that it's not just to compare these two values, we need a mean comparison. So in order to get a mean comparison, with right click, we're going to insert a chart. So we're going to use a box and whisker chart. And there are like 4 steps, but the most important step is the last one, step number 4. So step 2 and 3, they are just basically for labels and names of the scenarios. So I'm not going to modify these values here right now. But for the 4th step, this user form, it's relevant. Because here is where we identify the best scenario. So we need to click that we want to identify the best scenario. And we need to provide to process analyzer if we want to maximize or minimize. So basically, if we are maximizing, bigger is better, and we are minimizing, smaller is better. So in this particular case, we're using processing overall cycle times, so smaller is better. Smaller is better. The error tolerance means the difference in the means that you are willing to accept. So in general, let's define at 0. So once we're done, now we ask process analyzer to show the best scenarios if there is one scenario. So it's saying that the second scenario is the best scenario here. There is like an statistical difference between our two scenarios. So we click on finish and we get our chart where if there is one scenario that is different, it will be marked in red. So in this case, the second scenario is the best scenario. So in the recommendations here, we will be able to conclude that if it's possible, we're going to increase the number of operators from 1 to 3 because it has an impact. So that's for part D. And now, the last part in our problem is part E, where we want to find the number of replications. So for the single operator scenario, we want to reduce the half width to the 5% of the mean value of the cycle time. And we want to use the approximation based on the standard normal critical value. So let's go to our presentation. Okay. So in part E, this is the equation that we need for the normal critical ratio that I mentioned. We know that our half width, the desired half width, it's the 5% of the overall cycle time. So we multiply the overall cycle time by 0.05. So we get that the desired half width is 161.8. Remember that the current value is 350.3. So in this equation, If we want to get n, we need z. So for the z value, we need a z table and the confidence level. So we're going to work at the 95%. So the z, it's 1.96. The s, or the standard deviation, it's 489.71. We found it for part C when we were comparing the confidence intervals. So, and the h, the half width, it's the target half width, it's 161.8. So we plug these values in the equation, and we get that the number of replications is 35.19. Remember that in general, the suggestion is to round up our numbers to the next integer. So, but this equation is suggesting that we need 36 replications in order to get a half bit closer to this value, to the 161.8. In general, we are not going to get exactly that value, but we should get a value that is close to the desired value. So that's everything for today. So I will see you in the next video.